In the previous video, we introduced ourselves to the idea of average atomic mass, which we began to realize could be very useful to think about a mass at an atomic level or at a molecular level. But what we're going to do in this video is connect it to the masses that we might actually see in a chemistry lab. You're very unlikely to be dealing with just one atom, or just a few atoms, or even just a few molecules. You're more likely to deal with several grams of an actual substance. So how do we go from the masses at an atomic scale to the masses of samples that you might see in an actual chemistry lab or our scale of the world? Well, the chemistry community has come up with a useful tool. Let's take lithium for example. We know its average atomic mass is 6.94 unified atomic mass units per atom of lithium. This isn't really useful to us directly because an atom is just so small that it is quite insignificant to know its individual weight. But what if there were a certain number of atoms of lithium such that if I have the atomic mass multiplied by a certain number of atoms, then I'll actually end up with 6.94 grams of lithium, which is much more useful on the human scale. Fortunately, there is a number like this, and this number of atoms is 6.0221415 times 10 to the 23rd power. So if you have a sample with this number of lithium atoms, that sample is going to have a mass of 6.94 grams. Whatever element's average atomic mass is in terms of unified atomic mass units, if you have that number of atoms, you will have a mass of that same number in terms of grams. Now you might be saying, is there a name for the number 6.0221415 times 10 to the 23rd power? And there is indeed a name, and it is called Avogadro's number, named in honor of the early 19th century Italian chemist Amedeo Avogadro. In most contexts, because you're not normally dealing with data with this many significant digits, we will usually approximate it as 6.022 times 10 to the 23rd power. Similar to how we round off pi to 3.14, even though it actually goes on much longer. Now there's another word that is very useful to familiarize yourself with in chemistry, and that is the idea of a mole. Now what is a mole? In other fields, it might be a little mark on your skin, or maybe a burrowing animal. But in a chemistry context, a mole is just saying that you have this much of something. It's a fixed amount of something. The word mole was first used by the German chemist Wilhelm Ostwald at the end of the 19th century, and he came up with the word because of its relation to a molecule. Now what does that mean? Well, think about the word dozen. If I say I've got a dozen eggs, how many eggs do I have? Well, if I have a dozen eggs, that means I have 12 eggs. A dozen will always be 12, no matter what object is being specified. So if I say I have a mole of lithium atoms, how many lithium atoms do I have? That means I have 6.0221415 times 10 to the 23rd lithium atoms. A mole will always be Avogadro's number, no matter which element we're using. It's the exact same idea, it's just that Avogadro's number is much more complex of a number than a dozen is. So now, let's use our newfound powers of the mole and Avogadro's number to start doing some useful things. Let's say that someone were to walk up to you and give you a 15.4 milligram sample of germanium. How many atoms of germanium am I dealing with? So we start off with 15.4 milligrams of germanium. The first step might be to convert this amount to grams of germanium, and so we can do a little bit of dimensional analysis. We can just multiply this for every 1 gram of germanium that is equivalent to 1,000 milligrams. And so if you essentially divide by 1,000, we're going to get the grams of germanium, and this turns out to be 0.0154 grams of germanium. And now that we have an expression for grams of germanium, we can think about moles of germanium. So how do we do that? Well, we're going to multiply by some quantity, and in the denominator, we're going to want grams of germanium, while in the numerator, we want the new expression to be in terms of moles of germanium. So 1 mole of germanium is equal to how many grams of germanium? Well, we see it right over here. Germanium's molar mass is 72.63 grams per mole. So for every mole of germanium, we have 72.63 grams of germanium. In an actual chemistry practice, finding out the moles of a substance might actually be the most useful thing. But if you wanted to find out the actual number of atoms of germanium that we're dealing with, we will just multiply by the number of atoms we have per mole. And this is going to be true for any element. For every mole, you have Avogadro's number of atoms. And we're going to approximate that it's 6.022 times 10 to the 23rd atoms of germanium for every 1 mole. So if you want to figure out how many moles there are in 0.0154 grams of germanium, it's going to be a very small fraction of a mole, because a mole is 72.63 grams when we're talking about germanium. We only have a small fraction of a gram of germanium, so obviously much less than 72.63 grams. And so we saw from our analysis that to figure out the number of moles that we have with 0.0154 grams of germanium, we have to divide that by 72.63, since that is the weight of one germanium mole. Once we do that, we end up with an extremely small number of 0.000212 moles. That is precisely the amount of moles worth of germanium that we have. And if we want to now figure out the number of atoms of germanium, we'll then multiply this minuscule number by Avogadro's number. So the final calculation would be 0.00212 times 6.022 times 10 to the 23rd. And then that will give us our final answer. When performing this calculation, we get a really complicated and long number, but if we round it off to the most significant digits, we're going to get 1.28 times 10 to the 20th atoms. So we have approximately 1.28 times 10 to the 20th atoms of germanium within the 15.8 milligram sample that we received, which is quite a lot. I'll leave you there because things are definitely getting quite complicated, especially if you've never done these calculations before. I don't expect you to be able to perform these formulas on the spot right now, but it'll come naturally with time as we perform more and more of them in future videos, as this is a pretty common calculation in chemistry classes. In the next video, we'll look at the different ways that we can represent a molecule through empirical, molecular, and structural formulas. But for now, I thank you all for watching.